I also have to excuse, I have to speak in English. I really am not fluent in French. So Russell already talked about the challenges construction is facing today. He talked about the shrinking workforce, productivity issues, and of course, the big issue of sustainability. And in my presentation, I want to pick up on that and talk about how automation and robotics might be able to help to tackle some of these problems. But I also want to address the challenges the industry faces in actually adopting these technologies. And I will do this from a perspective of our company, Rob Technologies, and some of the projects we've worked on over the last couple of years. So at Rob Technologies, we support manufacturers and construction companies in automating their production. So basically, we help them to solve their technical challenges in how to translate and adapt their processes towards automation and robotics, but also how to efficiently make the robot do what they want. And this is a decisive point because construction is quite different from other manufacturing industries. Basically, we will build one-offs, so buildings are built for a specific site, for a specific client. And in general, we have non-identical parts in the building. So we are challenged with a high mix and low volume. This means that we cannot use the same concepts of robotics applied to construction that we used in traditional automation, which has been driven by mass automation, mainly in the electronics and automotive industry. And this is especially true when it comes to programming or teaching a robot to perform a new task. And I mean, I experienced this firsthand back in 2005, still at ETH, when we got our hands on the first industrial robot arm, and we just wanted to perform a simple task of stacking some bricks. And we realized how laborious and costly it is to teach the robot a task. So in traditional automation, this can be neglected because you program the robot once and then it performs the same task 24/7, year in, year out. But when every part is different and you have to redo this process again and again, this approach is just not feasible. So with Rob Technologies, we concentrate on developing and providing software solutions that allow our clients to adapt their robotic processes very easily and quickly to new fabrication tasks themselves without any expert knowledge. And we do that by bridging what we call the fabrication gap. Russell also mentioned it in his talk that trying to get from the CID data that is produced directly to the robots. Because it's a paradox. So you have the digitally controlled machines like robots that can perform arbitrary fabrication tasks. On the other hand, you have highly advanced digital design and engineering tools, but these are disconnected. Moreover, engineering and design data mainly holds the geometry of the finished parts, but no information on how to actually produce and assemble these. So our software takes the CAD geometry data as an input and automatically derives from that all the processing steps and necessary assembly sequence to actually produce these parts. And in our opinion, this is pivotal because otherwise you have no chance to reach a productivity anywhere close to other manufacturing industries. Very first project where we were involved with and where we could apply this technology was the development for robotically assembled brick facade system. Our client here, qu'elles Systeme, is a brick manufacturer, and he also builds prefabricated facades. And the task for this process was not to mimic the manual bricklaying, but to exploit the potential of the robotic arm to position every individual brick. You have to imagine the effort and cost for the robot to place a brick is the same if he places them all in a straight line and on a perfect grid, or if he shifts every brick a little bit or rotates them. And something that's very difficult if you want to do it manually. And essential part of this process is the software. So this allows now a continuous use of the data from the design to the execution planning, where you do the panelization of the facade and define anchor points, to defining the production batch and eventually the control data for the robot. And if we look at the robotic process itself, it's not very demanding or complex. It's basically a pick and place of the bricks. So the value here is really in the software, which allows you to quickly and easily build up a three-dimensional facade where you have control over every individual brick. And this information you produce is directly connected to the fabrication. So the engineer or the architect that's drawing this facade in the background, without actually realizing, he's programming the robot to fabricate this element. The very first project that was realized with this technology is the winery Gantenbein in Flesch. And this facade was built over 10 years ago. And it's a pivotal project because it marks the first time application of an industrial robot in architecture. And it also showcases the potential of the robot to precisely position every brick. You see it allows to create patterns on the facade or images, something, again, if you would ask a manual bricklayer to do that, would be very hard and time-consuming. So over the years, our client Keller realized a number of projects. For example, there on the bottom right, you see an interior application for a small chamber music hall. And here, the brickwork combines aesthetic and functional requirements. So the pattern of the brickwork actually is such that all the walls act as a large diffuser, and it improves the acoustic qualities of the room. And combined, all of these projects show the scope of potential solutions. And this is made possible through software that connects the freedom of design with a highly flexible fabrication process. So all the facades you see here were designed and produced on the same robotic system using the same software with no need to reprogram these tools. So it really exemplifies how we can achieve industrial production for highly customized designs. Today, a majority of our clients are in timber construction. You're probably all aware that timber construction is on the rise because timber can play an important role in reducing the CO2 and energy mortgage of our buildings. This is a gantry robot engineered by the Swiss company Güdel. We were responsible, again, for the control software and automating the path from the design and production planning to the machine. This gantry robot was installed, and the first project that was built on it is this roof structure. It's a non-standard roof for the ITA building at ETH Höngerberg. That's actually the headquarters of the NCCR. So this roof features over 168 individual trusses that have a different geometry, and combined they form this doubly curved roof. And in the roof, there are over 50,000 slats that build up these trusses that are all cut to different lengths and at a different angle. And this roof was completely built, automated on the gantry system. So you can see here how the gantry picks up a slat. It is cut to the desired length. Then it places the slat in position and eventually connects the slats with nails. So all the connections in the roof are done just with nails. There are probably, I'm not sure, over 80,000 nails in this roof. Brussels means 500,000, that's even more. And every nail has a very precise point and location in the roof because that's necessary to make sure that to guarantee the structural soundness of the roof. So here's also where the precision of the robot became instrumental. Both the roof and the brick project demonstrate how robots can successfully be applied to automate complex designs and bespoke structures. And the processes are also similar, as they work with a large amount of relatively small members that are positioned in a complex relationship. And due to the sheer number and amount of parts, it's probably obvious that this would be really hard to do manually. So here, the robot becomes instrumental in producing these structures, and the robot can, is able to hugely increase the productivity. Actually, the timber manufacturer who built the roof started out building these manually, and already having the pre-cut slats and just assembling the slats, it took him 120 man-hours for one single truss. In contrast, on the gantry, that also includes the pre-cutting of the slat, one truss could be built in 12 hours. So you have a productivity gain that is over 10-fold. So I think how interesting these projects are, we also have to be aware that this is probably not the main job construction is faced with. Well, these are niche projects. The roof itself is a one-off. And also the facades, there's only a small market and the scalability is limited. But the bulk of the jobs building construction has to deliver is quite different. In timber manufacturing, it's about this. It's about panelized timber frames for walls and floors. And these are actually also non-standard. I mean, they're based on the same constructive system, but all of these elements have a different dimension, different cutouts, depending on structural requirements, etc. So actually, the gantry you just saw that built these roof trusses, its main job is actually to produce these prefabricated wall and floor panels. And automating these processes, so you could say these are existing processes, normally they do this manually, now they put it on a gantry robot, and trying to achieve a considerable productivity gain is much, much harder. And for once, you have much more processes involved. If you think to the brickwork or also the roof, you just have two materials and two processes. You pick a brick and you glue it. For the roof, you have the timber slats that are cut to a certain length and then nailed together. If you think back to the image I showed at the beginning of how we generate all the assembly and processing information, just for a simple interior wall, there are over 10 different processing steps. And you also have a multitude of different materials involved. Just for the frame, you could have different types of timber depending on the structural requirements. You have the insulation. You have probably 2 to 3 different sheeting materials on a single wall panel. And then you have a lot of different joining processes and fastening processes involved, from gluing over nails, clamps, nails of different sizes. So here, the complexity is not in the geometry of the building elements we produce, but it's actually in the robotic process itself. And this is an image of a recent project we're working on right now. It's a highly automated timber frame panel production line. And I think just if you look at this image, it illustrates this challenge, how automating these processes is not only much more complex, but also much more costly. Or if you just look at the dimension of the system. And it integrates, for example, an automated warehouse system to handle the different materials and provide them at the right time, a CNC table for pre-cutting the slats, and also a end-of-beam trimming machine. So here we are not talking about simple robotic arms anymore. This also means this is capital intensive. Not every manufacturer can actually afford or is willing to invest in such a system. And if we look at the productivity, here we can achieve a throughput increase of 44%. That is actually quite respectable, but it's of course far off the factor 10 we've seen for the roof trusses. And for once, this is of course because we're still talking about lot size 1. That means all of the panels coming out are different. And we're also comparing this to the way our client is currently working. And here we have to say, especially in Switzerland, in timber manufacturing, they already have highly optimized processes in place. So all the manual production lines are very, very efficient, and they also already make use of CNC machinery and multifunction tables. But the motivation of our client here, of course, it was to reach a higher throughput, but it's also to build up security against shrinking workforce and become less dependent on skilled labor, because this is an issue he's already experiencing today. So now at the end of my presentation, I want to share the next steps we're taking as a company. Now we're actually switching roles from an enabler of automation to that of a producer or manufacturer. Together with the engineering company ZPF of Basel, we are joining starting a joint venture with our aim to develop, market, and produce highly sustainable floor slab systems. And the reason for us to take the steps are manifold. For once, over the years, we experienced that if we really want to drive change in the industry, we have to have more control over the complete process. But much more, of course, we believe that this is a product with high value. It is scalable and thus can have really impact on the construction industry. The idea originated from a concrete building project being realized in Basel in the next 2 years. And here, from the outset, it was to minimize the ecological footprint that was central to the design. And the focus was on minimizing embedded energy and carbons of all the materials and structures used. And if you look at structural elements of a building, floors and ceilings actually present a huge leverage, because 70% of a building, structure, are floors. So for that reason, the focus quickly was laid on the floor system, and the engineers developed a hybrid timber earth floor slab system that matches performance of a concrete slab, but features 80% less embodied carbon. And here the earth plays a vital role, because if you compare it to maybe alternatives in purely timber, we introduce mass into the system with the earth, and this mass can be used once it can be activated, thermally activated, so it can be used for passive cooling and heating of the spaces. It's beneficial for acoustics, for sound insulation, and it plays a vital role in fire protection of our whole ceiling system. And this chart actually illustrates the reason why we then looked into automation. This compares different floor slab system, which were all analyzed for this building project. So we really compare systems that all perform the same regarding payload, fire resistance, and acoustics. And what it shows, what is kind of strange, you have the flat concrete slab, which really spikes out if we look at the primary energy usage and global warming potential features. Even in regards to a ribbed concrete floor, because this the straight concrete floor slab is just not optimized with the material. Also, Russell briefly touched upon that point. But still, in 80% of all projects, that is the slab of choice, because it's easiest to produce and it's the cheapest. Although, if you compare costs, it's not even that big a difference. It's around 10 to 20%. But this illustrates actually that in construction, if you come down to it, the sole driver is costs. So we realized if we really want to have an impact, we have to come to a competitive price with this system. I mean, the earth material itself comes at nearly no cost. You can use excavation material. But the processing and ramming of the earth, which is traditionally done manually, as you see here, how it was done for our first prototype, is very strenuous, labor-intensive, and therefore costly. So we started looking into how to automate this process with robots. And we are now able to demonstrate that through using robots, we can considerably increase the production speed, reaching a cycle time of around 1 minute per square meter for one of these floor slabs. So here, automation and robotics is crucial to allow us to offer floor slab with what we think superior performance, but at a compatible price. And this floor slab was fully tested, so it satisfies all separation criteria between independent units, which makes it ideally suited also for multi-residential housing. Moreover, it's fully circular. Solid timber beams, there's no glue involved, and the earth can directly be reused after end of life, or being organic materials can be returned into the biological cycle. And with this, I want to conclude. Here with this project, automation and robotics, through increasing efficiency and productivity, can play a vital role in addressing the main challenges of the industry, which are, on the one hand, decarbonizing construction and become less wasteful, so to move from a linear to a circular industry. Thank you very much.